we learned about LOL diagrams. And we started with this first problem, where we have a car on a frictionless roller coaster track launched by a huge spring. I just want to review this problem before we look at 2, 3, and 4, which are variations on this problem. In this problem, we are told that the cart, earth, track, and spring are all a part of our system, so we add that to the O of the LOL diagram. We set our reference level to be the bottom of the track, and we said that our object starts out only with elastic potential energy, and in the final scenario has both kinetic and gravitational potential energy. In this scenario, I chose 4 blocks for elastic potential energy to begin with, and I randomly said that kinetic and gravitational potential energy would be equal at that point, each with 2 blocks. Again, the number of blocks that you choose is completely irrelevant. It's just important that the number of blocks you have in your initial graph are equal to the number of blocks you have in your final graph. Let's take a look at a slight variation on this scenario. In number 2, we have the same cart on the same track, but this time we're told to repeat it with the spring outside of our system. In other words, our system would contain the cart, the earth, and the track. And the spring would be labeled as outside our system. Because the spring is outside of our system, it's exerting a force on our system. And we'll use an arrow and the label for that force to indicate that. Because it's a spring, the type of force that it exerts is called the spring force, or F sub S. Again, I need to set my reference level. And I'll choose it the same. Initially, my car is still not moving. And initially, my car is still at the reference level. However, this time, because the spring is outside of my system, my initial energy, I do not have any elastic potential energy initially. To have elastic potential energy, the spring must be a part of the system. So in this case, there is no elastic potential energy to start off with. In my final scenario, my car is moving, and it is no longer at the reference level, so it has both kinetic and gravitational potential energy. My spring is still not a part of my system, so I can't have any elastic potential energy, and my track is still frictionless, so I have no thermal energy. Just as before, I still have 2 blocks of kinetic energy and 2 blocks of gravitational potential energy at the end, but this time, that energy came from the spring force, an external force on the system. When there's a force adding energy to or taking energy away from our system, we say that that force does work. And we indicate that in our equation by saying the work done by the spring force is equal to the final kinetic energy plus the final gravitational potential energy. The spring force added energy to my system, thereby ending up in kinetic and gravitational potential energy in the end. Anytime you have work from an external force, it'll always appear on the left-hand side of your equation. Notice that we don't need an initial with that work. Look at another scenario. Going back to this, one other comment. Notice how the number of blocks that are in my initial graph do not match the number of blocks in my final graph? That will always be the case if there is an external force doing work on your system. If there is no external force doing work on your system, the total number of blocks must be the same. Now let's move on to number 3. In number 3, we're repeating problem 1 once again, but this time we have friction. So since we're going back to number 1, our system contains the cart, the earth, the track, and the spring. We'll keep our reference level where it was initially. Our object still has no kinetic energy at the beginning because it's not moving, has no gravitational potential energy at the beginning because it's at the reference level. And since our spring is back to being in our system, it does start out with elastic potential energy. Since it's the same scenario as number 1, you want to keep your number of blocks consistent between number 3 and number 1. Now in the end, we know in the final situation it is moving. It is no longer at the reference level, so it has both kinetic and gravitational potential energy. The spring is no longer compressed or stretched, so there is no elastic potential energy. But this time, since there's friction, there is thermal energy. if I think about this scenario in the real world, I know that friction, which is what causes thermal energy, slows things down. So that tells me that there would be less kinetic energy in this scenario. However, I also know that gravitational potential energy depends on the mass and the height, and those things don't change due to friction. So I'll have the same amount of gravitational potential energy as I had in number 1. Now, because I started out with 4 blocks, I need 4 blocks over here, so that last block would go toward thermal energy. When I'm writing my equation, I have that the initial elastic potential energy equals the final kinetic energy plus the final gravitational potential energy plus the change in thermal energy. Because this is a change in energy, you don't need a final on your thermal energy symbol. Our last scenario here simply changes where our final snapshot is located. This time, in that final snapshot, the car is only halfway up the loop. Since we're repeating number 1, we still have the cart, the track, the earth, and the spring in our system. Our reference level is still this level ground here. Our object is still starting out with no kinetic energy, no gravitational potential energy, but the same amount of elastic potential energy as we had in number 1. And then in our final scenario, the thing that has changed, our car definitely has kinetic energy, definitely has gravitational potential energy, doesn't have elastic potential energy, and since we're going back to number 1, is frictionless and therefore doesn't have any thermal energy. It says to make sure the bars are scaled consistently between problems 1 and 4. So, since my car is only halfway up the loop, its height is half of what it was in number 1, which means its gravitational potential energy is half of what it was in number 1. That extra block of energy then would be added to kinetic energy in this case. When writing out my equation, you'll see the equation looks the exact same as it did in number 1. That the initial elastic potential energy equals the final kinetic energy plus the final gravitational potential energy. Overall, some things to make sure of. When you're drawing these diagrams, the number of blocks in your 2 L's should be equal unless there is an external force doing work on the system, in which case the number of blocks should not be equal. Knowing whether or not there's an external force doing work on the system really depends on the scenario. Sometimes you'll look at the scenario and determine that there's no kinetic energy, no gravitational potential energy, and no elastic potential energy. So there must be some external force doing work on the system. Also, another quick note, when we're dealing with elastic potential energy with these LOL diagrams, typically we have a spring that's being deformed. If you don't see a spring in your problem, the problem would have to be really specific in saying that an object is deformed for there to be elastic potential energy. Now that we've learned a bit about these LOL diagrams, it's time to try it out.